Gut, irgendwie passiert da oben nichts, oder? Aber der hat sich eingeschaltet. Morning. So, let's wait a moment for the projector to switch on. I hope it's, yep, it's just very slow. Na, verdammt. I don't know, but the thing is, the lamp seems to be lit. It's only not getting warm. This thing must be decades old. I see something. Is there something coming? I'm not sure. So the power is switched on. I think it's making noise now, which it hasn't done before. If I press the power button, I need a stick for that. This thing is most annoying, but I mean, it should at least show some blue picture or something. I even brought a new HDMI cable this time. Oh, now I see something happening. It's slowly, at least you see now a reflection on the lens. No. Okay, I can. Maybe it switched on the wrong input or something. Okay. Yes. Safety notice, don't do that at home. Aha. Enter, where's the input button? Okay, then at least it tries to do something, so maybe I try the other cable. Let's try this one. Okay. So, okay. So, you might have already seen this here. I think I've showed you this together. I've put this together, and what we've added for today morning, what we add today is pseudo time and kernel smoothing. So you can look at these last two links if you want to read along while I show this here. So what today we want to use, I've had some trouble with example data set we used last time. So this time I use a slightly different example data set, namely that one here, which is also Anna's group. It's more or less the same kind of experiment. Again, stem cells, astrocytes, and immature neurons taken from the subventricular zone with a mouse. Only this time it's a different mutation. It's not an interferon stimulation receptor as we had last time, but this time it's a knockout of the interferon receptor. So specifically of a double knockout of both interferon receptors. So it's called EF narco or interferon alpha gamma receptor knockout. And they wanted to see how much this stem cell, because that's the Martin Lab's current hypothesis, that this whole activation of quiescent neural stem cells is somehow interferon regulated. So they have knocked out these things and they have published here a paper on what they found. I'm on the paper, so I should probably be more positive, but actually I find it pretty inconclusive and I still don't quite know what we've actually found out. But for us, let's have a look at this now. I load the data here. We go through the different stuff. And then what we want to do today is that before we had always looked here at the clusters. And that you already know from previous lectures, so we don't really go through that. I loaded the data, I did my Leiden clustering, and now we can look into every single of these clusters and compare the markers or take these whole blobs together and say what's the markers of this against the other. Instead of doing this, we use a cheat code. Namely, we use the fact that Damian, who's the first author of the paper, has already done all this for us. And so we just look at his results. So here you see what he has found. He has said that this here is the lineage, with starting here with the quiescent stem cells and a couple of astrocytes from the olfactory bulb, that I think are the blue ones here. And you see the astrocytes and the quiescent stem cells are pretty similar. And when we proceed here through the quiescent stem cells of type 2 that are sort of more active looking, which don't exactly look like an astrocyte, but only roughly. When we activated astrocytes, which sit here, when we have here the transient amplifying progenitor cells, so these are the stem cells which got activated and now make cell cycle. And when we go here into the neuroblasts. And again, you see here, there seems to be a jump from the taps to the neuroblasts, which if you twiddle along enough with the UMAP settings, it can change. In the end, we also caught a couple of neurons, what is this here? OECs? I knew what OEC means. It's not all OPC, it could either be a type, no, it's not a typo for oligodendrocyte precursor cells. But whatever, only a bit of other stuff. Interestingly enough, he ran his own UMAP, and his UMAP looks a bit different than ours. Maybe he used different settings in the pre-processing. For example, this gap isn't there here. But what I now want to do is I just want to look at this lineage from quiescent stem cells type 1, type 2 activated stem cells, TAPs and neuroblasts. Damian and the others call this the lineage, because these are all the cells which are progeny of each other, while all the other colors are different stuff. So we want to understand how gene changed during the lineage. And we consider this now not as a bunch of different clusters with clear boundaries, but rather as a continuous change. We imagine that a cell starts as a QNAC1, then due to some triggering, which may or may not be interferon, it turns into this QNAC2, which is a quiescent cell ready to be activated, which when becomes activated, starts amplifying and doing cell cycle. This here, I think, is the cell cycle, and then jumps into becoming out of a cell cycle and jumps into becoming a neuroblast and finally a neuron. Or in this one here, from here going through this to that one. And we just want to consider this instead of a succession of discrete clusters with clear boundaries. We want to consider it as one continuous trajectory. This is because you remember from last time, our Louvain algorithm is sort of bound to always make boundaries. If you would have a long pipe, or sort of a long tube, something like this. And in this long tube, the Louvain algorithm wants to divide this up into two clusters. It won't change much the modularity score where exactly it will put the boundary. And this will then just be some random things about how we sampled our cells. So whenever we have something which in state space or in this PCA space is not clearly localized clusters of high density with areas of low or no cells between, but rather some elongated manifold, when it makes sense to imagine this elongated manifold as one continuous trajectory. And because in biology, such elongated manifold often show a temporal order, we call the main coordinate along this manifold with pseudotime. Because you can imagine what we see here, each one is a different cell, but we could also consider this as a snapshot of one cell starting here and slowly moving along this trajectory, along its life journey from being a stem cell towards becoming a neuroblast. In physics, we call this, we have this concept of ergodicity, where we say if we have a steady state system, when the ensemble average is equal to the temporal average. So if you have a steady state system where over time everything stays the same, like cells are born, cells progress, cells die, and overall the total amount of cell is the same. So if we do have a steady state system, which is a big if, but if we have a steady state system, we can say that we will get the same distribution depending on, no matter whether we just follow one cell through its life cycle, or if we or if we just take an average over all of them. This is strictly only true if A, the system is steady state, and B, if it's sort of stochastic in the sense that in principle every cell can end up everywhere. So it's not true here because we cannot become different cell types, and once the cell is here, it cannot go back. So this is more a concept from statistical physics, which sort of influences the whole thing, but isn't really true, and something we have to keep in mind that A, this is not a diffusive system where we can go from A to B, but nevertheless, we somehow try to use this here. What we really want to understand is the biology of a cell along its lifetime journey. What we have is a single time snap point, and we hope that we find instances of every individual data point here, and that by connecting all these cells, we go through along these things. And what we want to do for this purpose is that we want to find a point which coordinates along here. Now, quickly try something new. Yes, I mean, this is in a way what I said before, everything can go to everybody, and there is the so-called balance condition, and now we can go into a bit more about the stochastics modeling. In a way, I just wanted to throw the term in where the idea comes from, but exactly, the people who do macros will tell you what conditions we really need to see ergodicity. So the reason why I've switched this thing on here now is in the hope that it will record my board, so that this is now in the screening here. If we have a point like for example this here, what we now want is to somehow find a curve which goes through these things, such that every point here gets a number between, say, 0 and 1, or it could also be 0 and 10, or whatever you want, such that the number tells us how long we progress here. And there is two common aspects how to do this. One is based on the idea of principal curves, and I think I've mentioned this before. We try to find an actual curve through our space, such that if we project each cell onto this thing, that when the variance of all these points here gets maximized in a certain sense. And so we try to find a curve which is not too wiggly, but sort of smooth, and which goes, and which has this property. And the other possibility is, that's also commonly used, is called a diffusion pseudotime, where we assume a diffusion process where we put probability weight on one of a cell which we think might be the beginning of the whole thing. And when we imagine what is the probability to get from this point to any other point within one hop through our neighborhood graph? You remember the neighborhood graph of last time, where we can sit on any point and we can make a hop on the neighborhood graph and hop to another one. And we iterate this and ask, what's the probability to reach this cell, starting here in 2, 3, 4, 5 hops. And in that way, for each number of hops, I can make a probability distribution over this whole thing, which tells us how far we get. And the more hops we make, the further over we get. And this way tells us that, and so in the way we can imagine that this diffusion of starting here over there tells us something along these lines, because the diffusion will act along the longest action, while in this direction we will soon get an equilibrium after only a few hops with things happening back and forth. So we see a decay of probability going from 0 to 1, while we don't see a decay in the transverse direction. What you then typically do is you start with diffusion from both ends, and you have to somehow guess the ends before or find some heuristic to do it. And then you decide on a certain number of hops and say, okay, let's take 10 time steps, 10 hops, and then ask how much do these 2 points overlap? Sorry, no, that was wrong. If I want to get the distance, the diffusion distance between 2 points, say that point and that point, I start simultaneously diffusion processes, both of these points, and let it run for, say, 10 steps. And then I check how much do the two diffusion probabilities distributions overlap. You can imagine, the reason why it's called diffusion is because the underlying intuition is, let's imagine you have a filter paper or some blotting paper or so, and you put a color of, put red ink here and put blue ink here, and then you wait for a while, and as you know, you will get a Gaussian distribution of color intensity around your original point and here as well. And now you can define a distance measure between these 2 points by saying, after I wait for, say, 1 minute, how much have these two things flown into each other? And this is called the diffusion distance for 10 time steps, that I calculate 10 diffusion steps, and then I calculated the overlap between these two. Using the nearest neighbor graph, exactly. Yeah. Exactly. Yeah. And this is now a bit a preview of what we do next lecture, because then we'll just simulate this a bit and look how it actually looks like. For now, we just stick to what we have, because as we do this in high dimension. And before we do this in high dimension, I want to do it in 1 or 2D. And we will see an application for this 1 or 2D point in a moment. Yeah, the diffusion, the short thing, as I say, next time I will tell it in more distances. I have my neighborhood graph that we had last time, where we have edges from each to every other thing. Now we can keep our adjacency matrix as it is, and simply turn the adjacency matrix into a stochastic matrix by normalizing the columns. The idea is, if you put a probability mass of 1 on a point on a cell, and then you have a vector with zeros everywhere and a 1 at this point, at this cell, and then you multiply this to the right onto your adjacency matrix. And afterwards, you have a vector which has 1s at all the neighbors. If you have before column normalized your matrix, or made it a stochastic matrix, as the statisticians have said, afterwards, your matrix is just a distribution of saying, okay, with probability 1/4 it has ended here, with 1/4 it has ended here, and so on. So that's what we do. We take the adjacency matrix, we divide each element by the column sum, so that afterwards it's what they call a stochastic matrix, which describes a Markov process. And then we can by this run weight. And we multiply it through several times through the matrix. So take the matrix to the kth power. And then I get a vector in the end, which tells us how far after 10 iterations. So if A is our adjacency matrix, and we row skull normalize this to get our transition matrix, let's call it S. And then we take S to the K, or I call it capital T, the number of time steps, times an initial vector V, which, let's call it an indicator matrix. So Vi is, let's say, how do I best write it? I want a vector Vi, I simply call it EI. It's the ith unit vector, which marks cell I with a 1 and everything else with a 0. And I multiply it to the right 10 times or t times with this thing, and then I get the probability distribution, how far I can go from the cell by diffusing through, by hopping through the adjacency matrix to go go anywhere else. One thing I can do is that what I often do is that I don't just keep the adjacency matrix as it is, but put a bit the weight in. So I replace the ones by the distance under a Gaussian kernel, so that we are hopping more nicely, that we say the probability for hopping from here to anywhere else is given by given by the distance run through a Gaussian. I'll write this down properly next time. For now, I want to leave it at that. But the point which you're probably missing is I do this from one point. I want to define what I call the diffusion distance between dist between two cells I and J. And what I do for this is I take my two transition matrices of these 2 points and check how strong do they overlap. This function f here, to compare the two distributions, typically people use the Kullback-Leibler divergence. So let's call this dkl. And as I said, for this s here, we typically use something like Sij is e to v dij durch sigma squared so I say the probability of hopping from I to J is given by a Gaussian kernel, which takes the distance from I to J with some kernel with sigma, dy, and of course normalized so that we end up somewhere. And with sigma, we typically do that most of the kernel sits around that most of the weight sits within the 20 nearest neighbors or so. But let's better switch over to the 1D part, because that's the part I have properly prepared. The purpose is to define a distance from each, the purpose of this is, I really shouldn't have gotten into this. Damn it, should never start explaining something. The purpose is that this way I can define a distance from every cell to every other cell. And if I now take here the distance of the cell I towards the last cell, and this here is the distance of a cell I towards the first cell, where I define some cell here, let's say this is the last one and this is the first one. So I select them. And if I now do this and plot for each cell the distance to the last and to the first cell, typically you would expect that you'll get something along like that here. Or typically it will, as we will see next time, look a bit like this. So that a cell sits either close to the last cell or close to the first cell, and then I can parameterize this curve and take this as my pseudotime. So that is my way of figuring out how far I'm along that by taking each cell and asking, does it take longer to diffuse from this cell to the beginning or to the end? So, yeah.
So how do you know these curves are unique?
This is X.
Something like
they aren't. They aren't. And no, this is exactly, sorry Andreas, please leave this to next time. Just try not to think about it and instead think about the stuff that we now do here. Next. I know this was a bad idea to start with this. Anyway, so what I have now done here is let's try the adapter again. This finished, I think we made. So, what we now do is, as I said, there is these two possibilities, the diffusion pseudotime and the principal curves. I should have left it at just saying there's two possibilities, which we'll discuss next time. The diffusion pseudotime is what Damien used in the paper. So, and yes, you can see here what we then get is that we start here at 0 and end here with 1. And there's some way of getting from here to here. And all these points are sort of considered the same time, or this is considered the same time. So I use the color here to consider the time. And as you can see, it's not always as it looks like in the UMIP. So for example, this part seems to be earlier than that part. And here's a tiny blue one, which seems to be here, like it all seems to turn into a circle. And you get a lot of strange surprises. And actually, and here is, sorry, no, this was, here is the diffusion pseudotime plotted into Damien's own UMAP, where it looks even weirder. So that's how it is in the paper. That here it seems that the pseudotime looks backwards. So in the paper, we would argue that the UMAP has made a mistake and that this thing here actually should be here. Whether it was the UMAP that made a mistake or the pseudotime, we don't know. Yeah.
Okay. I'm just wondering, it's not like, it doesn't always need to be linear, right? It's like,
that's the other points, yes. Okay, I'm again getting into opening cans of worms, which we shouldn't. So,
I mean, there are many parameters.
Exactly, this is why we leave the whole thing out. So, because what I actually had planned for today is to use this pseudotime only as a means to get a 1D parameter which we attach to each cell, wherever it may come from. And then we go into smoothing. The reason why I want to explain 1D smoothing before getting into this pseudotime is because the principal curves can only be explained if you know about kernel smoothing methods and about local regression. So let's start with that. Also because local regression, apart from being a part of using principal curves, it's also something we need for its own right. So here is now my attempt to use this other method, the principal curve method, where we try to find a curve through this 30-dimensional principal PCA space. And this curve is parameterized from 0 to 1, and every point is projected onto this curve. And as you can see, it has now found this way here. And just to quickly show how this actually looks like, I think we can do this now in the actuals. In the actual selection of highly variable genes, PCA, and so on. That's all as we've always done. And yeah, we have this. Yeah, exactly. So this is the pseudotime of last time. Let's see if I have bought an adapter this time. Let's see which one works better. So this is the curve we've just done. And if you look at how I've done this principal curve algorithm is rather slow, so I didn't want to do it for all my 20,000 cells. So I took a subset of 2,000 cells. One thing you will see several times is this line in my stuff. This is a random seed. Who knows what a random seed is? Okay, or who knows not? I should ask that way. Who needs to know? Nobody dares to. Yeah. So the basic point is, as you might know, whenever we use randomness in a computer, we don't have true randomness because the computer, being a deterministic machine, is using what's called a pseudo-random number generator, or PRNG. And the pseudo-random number generator is just a complicated iterated formula which takes one integer value and produces another integer value. And the formula attempts to be so convoluted and complicated that it looks actually random. And there's been considerable research going on in the 70s and 80s about how to find a deterministic formula, which is just a function which maps a integer in a given range, typically from 0 to 32, to another one in the same range, so which is essentially a bijection in within this space of integer between 0 and 2 to the 32 minus 1, so all the integers which fit into your word length, and that looks as random as possible. And typically when you use R, whenever you use any kind of function which uses random, like asking it to give you a random number, so for example here, it will call this random number generator, generate a integer, and use this integer then to calculate your actual random number by running it through a suitable transformation. And so this random number generator always has a given state, and this state will what random number you will get depends on the state. So if I call R norm again, it gives me different numbers because each time it calls a number, it stores the result, the new big integer it got, as its current state. And when I ask for the next time a random number, it uses this number, puts it into a complicated formula, and gets a new number. And to give you at least a buzzword of what these typical big random number formulas are, this is the one that most people use, the so-called random Mersenne twister. I don't try it, as if somebody of you is curious how the Mersenne twister works. Here you find it. And but the point why this is now important for us is the Mersenne twister, as I said, it's a function of all the integers in our bit range to itself, and we iterate it. So every time we want a new function, we take the result of we take the previous number and put it through to get the next number, and again and again. And the question is, what number do we start with? And typically computers initialize the random number generator with something which is, if not random, then it's at least unpredictable, such as, for example, the number of microseconds which have been passed since the computer was switched on is a very popular one, which I think is what R uses. But what I can also tell is, say, set the random number generator to use this number. Okay. New try. Shouldn't be too big. I said it should fit into 32 bits. So if I now use this and I call R norm, I'll call it again, and I get this, now I set back to this random number generator. And as you can see, now I get the exact same random numbers again, which is terribly useful if you prepare lecture notes like this, because you don't want to always things switch a little bit. For example, something which I've noticed with the Louvain clustering that we did last time is every time I run it, the cluster numbers change slightly. There was a cluster which is half of the time is called 12, the other is 13. After I put a set seed in front of it, it didn't change anymore because the iGrive package internally uses this random number generator.
I was wondering how the clustering algorithm works, or how it determines the first number. So apparently it's random. It's completely random, or is it
It seems to be, yes, the clustering algorithm seems to use some randomization at some point. This is an old point in computer science that randomization often speeds up things, because often you might have to choose some initial value from which you improve, and there might be an obvious choice of just numbering things from 1 to n. But when you might run afoul from the fact that your data might have been a predetermined structure, maybe the cells were sorted by size or sorted by something else, and if you are unlucky, this actually counters the thing. With the pre-ordering of your data actually bites with the initial value of your algorithm, so that it's just the worst possible starting point, and this is much less likely to happen, or virtually impossible to happen, if you use a random initial state, if you pick a random initial state from a large enough things. This is why very many numerical algorithms, even those which are supposed to give you a fixed result, start with a random number, and you will see slight changes if you don't set the seed. A practical issue that you have to be sure that the function you're calling is using the same random number generator as the seed is set here. For example, here with UMAP, I think, does, other things don't, because your R function might call some C function, which might call some other random number generator, and when it doesn't mesh. Another issue is if you work with multiple CPUs, when you get so-called race conditions, where the two CPUs always ask a random number generator independent of each other. And so when, depending on the microseconds in which the order of the two processes work, you get different results. But for us now, it's very easy. I have just used this number, which has been carefully chosen to give me some nice typing rhythm, 1, 3, 2, 4. And I always use this now. So I use this to sample always the same 2000 cells. And now I call this principal curve package, which, as you can see, calls here, takes here the PCA coordinated for this. It shows us here how the sum of the squared distances of the cells to the line gets lower and lower, and after 10 iterations it decides that this is now good enough. That's what the trace does. And the f equals 10 means it uses a smoother called, there's two common ways of using smoothing, called spline smoothing and local regression. This thing here uses a spline smoother, which doesn't fit with what I do next, because I'll explain to you instead local regression. But the principal curve can use both the spline smoother and the local regression. And the spline smoother is essentially the number of bends it can have that I put here. And with that, I now get my plot. Here is my plot. As you can see, these are the 2000 cells which I put. And just as we are about random little programming tips, when I did this the first time, I got this plot here, where you can hardly see the points, because the 2000 points get, of course, all overplotted by the 18,000 gray points. So I added this little trick and told it, before handing it to the plot function, sort my data table so that those where the pseudo time is not NA are plotted last. Because as you can see here before, this principal component function here gives me, this principal curve function here gives me, as you can see, here a, sorry, I've forgotten my mouse today, and I'm really clumsy with a touchpad. So this is all a bit complicated, unless somebody has a mouse by chance in Pocket. PRCS. So as you can see here, this is what the principal curve package does. It gives us for each of our 2000 points its projection onto the 30 dimension, its projection onto the curve. So this is sort of a curve defined as a long polyline of connecting each with the next. This here is for each cell where it is, what pseudo time it is. Calculated as sort of the curve integral distance from the start. Here, this is the ordering, in which order the cells appear in this thing, and so on, and whether it has designed. And I use now here this lambda, so the pseudo time. And as you can see, with this n frame, I can sag mal heute I can turn the whole thing into a table so that I can left join it to the thing, and then I can sort the whole table with so that all rows, which I really hate not having a mouse. It's terrible. I'm so clumsy with this thing. So now you can see here the cells and the UMAP coordinates and pseudotime where we have it, and after this arrange the rows with pseudotime are at the end and plot it on top, and I can nicely see it. So, as you can see here, for example, in this case, we start out here and we see here now this strange thing that we can now ask, is there a branching or is it really linear? Or maybe it didn't work because there's branching, which actually, the paper is out, but I think I still should have a second look at that now that I noticed that. And I compared here the pseudotime plotted for each of my cells, the pseudotime according to the paper with the pseudotime according to principal curve. And you can see there is clearly some connections between the two, but calling it an agreement would be too much. Which shows you that this whole pseudotime thing is a tricky part. And as you can already guess, a big issue of the part is what happens if the cells start initially and do what cells like to do by differentiating, mainly making a fate decision, whether they want to transform into this type of neuroblasts or that type of neuroblasts. And then we have what we call a branching. And then, of course, it's not appropriate to make one curve. We want curve which somehow forks and then ends in two things. And that's a big issue. But before we get into this, we just now simply decide, okay, probably Damian did it right because after all, that's the published result and I did it wrong. And let's stick with the pseudotime and ask what can we do with this pseudotime. And the first thing we might ask is what's actually changing while the cell matures? And in order to see what is changing, we might ask how does gene expression change? And I want to look at one gene which is very important, solute carrier 1 alpha 3, which is the gene coding for GLAST. And this gene is the one whose protein we used as a marker to find our astrocytes and stem cells and early progeny. And here you see how it's expressed. And I hope you can see this a bit. Here in the astrocyte and quiescent stem cell area, you see a few green dots, and then the dots get sparser and sparser, while here they turn up again. And better way to plot it, it would maybe be to give up on the actual expression difference and just dichotomize it in saying, okay, is it zero or is it not zero? And now you see here the non-zero ones as dots, which people like to call this a salt and pepper situation, when you have these few pepper strikes in a sea of salt. And what we really want to know is does the density of these dots in the graphing decrease smoothly or abruptly on going over there? And to see this, what I now do, and which is the obvious thing how we can use our pseudotime, I plot the LFRAX expression against the pseudotime. So these are now only those cells where I have a diffusion pseudotime, so the cells in the lineage. And here you can see how they sit there. And actually you can't see much because we have this big drop here of cells which have zero expression. And it's really hard to say where this sits. It gets even worse when you remember when you no, let's stick to this. It's because what we now want to do is we want to smooth this in a way that for each pseudotime we get a clear value, which is something like a diff we average over these expressions. And to do that, what I first start with is I start with a simple thing and then we'll become progressively more sophisticated over the next hour. And the simple thing I could do is that I just split this pseudotime into 50 bins and just take the average of the expression values of all the cells with a pseudotime between 0.0 and 0.005 and so on. And that's what I've done here. I take my pseudotime, I sort all the cells by pseudotime. And I divide the pseudotime. I could now do two things. I could either just divide the pseudotime by bins pseudotime 0 to 0.1, 0.1 to 0.2. What I've done here instead is that I try to make each bin contain the same number of cells. So I want the first bin contain the first 50, the next bin the next 50. This is why I sorted by pseudo time. And now I take the row number, divide it by 50, so that the first and floor is a function which rounds down to the nearest integer downwards. So that if I do this, then all those, the first 50 get bin 0, the next 50 get bin 1, and so on. I can group by this. And then summarize by taking the mean over the expression over all these 50 for each bin. So each one here is now a mean over 50 cells, and I take the mean over the pseudo time and over the expression, and then I calculate my value here. And now we can see it looks a bit better, but we still have this issue that often there's 50 cells which are all 0, so even the mean is 50, and somehow this is still not quite that useful. Here, for example, it's really hard to say whether the expression goes a bit up again or whether this is just an artifact, because we can't see how many zeros there are. Another issue is that remember how we calculated this log expression. We always said we take the counts k, divided by the total sum s, multiply with 10 to the 4, add 1, and take the log of that. And we did this so that if k is 0, we don't get minus infinity. But of course, this means that this 10 to the 4 enters some arbitrariness, and why this is an issue becomes pretty obvious if I replace the 10 to the 4 with the 10 to the 5, as I've done here. Here I've recalculated the normalization and just used 10 to the 5. And as you can see now, the plot actually looks markedly different than that plot here. And they kind of disturb us a bit. So we need a more controlled thing. And the more controlled thing technically is easy. We use the logfit package. We call this magic logfit function. And the logfit function has a Poisson family, which then produces us this fit. And what you might hopefully want to know is what does this logfit do internally. And for this, I switch over now to the other notebook. This one here. So. What I've done here is I've decided all these things are easy to understand, but when you know the ground truth, we don't know how the curve works, which we are trying to figure out here. But we can, of course, make ourselves a nice example where we know what's going on, and then we add noise and try to reconstruct what was there before the noise. And this is generally a very valuable way to work if you want to understand numerical techniques. So, but simulating data, which looks realistically, is not so easy. So I've decided to start with this function here. You see this function, I've carefully designed it so that it has a couple of challenging things, like our expression ramps up slowly over pseudo time, then drops very abruptly, then stays close to 0, and then it goes slowly up again. Writing an R function which produces this kind of data was a bit tricky and required a bit of fiddling with these numbers here and using splines. I don't explain how this works now. Even for the splines are a very interesting topic. Maybe we come to this later. For now, let's just say we have here a function which is called true function, which is the true expected expression for each pseudo time. And it works somehow, but it produces this graph. What we now do is we want to choose cells, and let's say our cells sit uniformly along the pseudo time. So whereas for the probability for each pseudo time is the same. So I take here 100 numbers between 0 and 1. And these 100 numbers sit here, and for each of these 100 numbers, I calculate the true function. And of course, if I did it like this, the whole thing would not be very surprising. We get this here. The same curve as before, only spotty. But to make it not so easy, I add random noise. And I add my random noise with a normal distribution drawn from a normal distribution which means 0. So I can overshoot or undershoot with equal probability. And the standard deviation is 0.1. so that this curve changes into that curve. And as you see, we now have here a noise of about 0.1 around the curve. And our aim is now, can we get back to the original curve? And let's start by doing exactly the same that we've done, that we've already tried. I make a plot. I make I bin the x-axis by putting each x-axis here in bins of always a 10. So I have 10 bins. This time I didn't, I cut the x-axis directly instead of putting always 10 together, but you can imagine that makes the same because it's uniform. We chose x from a uniform distribution anyway. So I group, I calculate the mean. Now I have here for each thing the mean of x and y, and the mean of x is as expected always more or less in the middle of the bin. And if I now do this, I get a reasonable picture of the curve we had initially. But it looks a bit simplistic, this way of binning and so on. So can we do better? Especially, this is not exactly what we would want in smoothing. It's not a continuous curve. It's a couple of individual points. Maybe I make it a bit smaller, then we have a bit more plot here. So this is here now really simply here always splitting this x-axis in 10 bins, and for each bin taking the averages of x and y and putting them together. Let's do something more sophisticated, and the standard thing that people like to do is what's called the kernel smoothing. Kernel smoothing means we want to have a continuous curve which I call f smoothed, where for every point x naught can be any point between 0 and 1, not only the points we have data for, but everything. And for every point x naught, we want to find a y value such that we get a continuous curve. And the way how we get this y value is that we average over the points in the vicinity of x naught. And in the simplest case, we could say we take everything from all the x values between x naught minus 0.05 till x naught plus 0.05 and make a mean over this. And here I've written it slightly more general. I say my value f naught is a weighted average over all the y values. And the trick is now that this weight function is, so this is my pseudo time or my x value, which goes from 0 to 1. And what you can, and let's say we request a smoothed estimate at this point x naught. What we now do is that we make what's called a kernel or smoothing window around this x naught and say, these are my weights. And for every point of the actual data points x, I calculate the weight according to this smooth curve and use this as a weighted expression. So that's what we have here. Wi is this weight. I'm sure the guy who came up with Gaussian processes was inspired by this old thing. So, as you can see here, this is what we do. Fk is my kernel function, my smoothing kernel. So this is this sort of Gaussian-shaped thing that I have used here. And this Gaussian-shaped thing has, of course, a center, x naught, and it has a width here, this thing here, or a half width. This here we call the kernel half width h, from here to here. And so I take my so to calculate this, the point at x naught, I take the average over all the y values, weighting each y value according to where this x value sits under the kernel. And for this to work, I have to define my kernel such that the function fk has this shape, 1, minus 1, So this is fk of u, and this is u. And u is the distance between x0 and x, rescaled by this division to h, such that the kernel is interrogated between -1 and 1. And I want a kernel that is 0 outside of these two smoothing points, so that I can say the average always runs only over those points which are within a distance of at least most h from our kernel value. And what shape should we use with this thing? When people started this, they felt the obvious choice is the Gaussian. And h was the standard deviation of the Gaussian. But that has a bit the issue. The Gaussian has these long tails which go up to infinity, which is actually not so bad, because for smoothing you might want that the smoothing window doesn't change suddenly. If a smoothing window tapers out slowly, that might be nice, but it's numerically very unnice, because you always have to look at all the data points for every individual point x0. So it's better to use a smoothing kernel which lists sits there. And here is a list of all the smoothing kernels that people like to use. And for the smoothing, people like to use this one here, the tricube kernel, which is missing in the picture here, but which is somewhere here. And here is the tricube kernel. And as you can see, the tricube kernel has this nice property that it starts, that its support is exactly from -1 to +1. Outside of its 0, it is continuous and differentiable here. And in the middle, it is sort of has a flat top, which is also nice because it sort of spreads things out a bit. The tricube kernel, I'm sure somebody just played a long time till he found something like that, which is differentiable here and flat here. And then they came up with this funny function, 1 minus absolute value of u cubed, and this whole thing to the cube. And I've put the normalization factor in front of it, 7081. This is just the integral of it. If you integrate from -infinity to infinity, or from -1 to 1, you get 81 over 70 for this thing. So we put it in front so that our smoothing kernel has weight 1. That is, of course, completely unimportant for us, and just for completeness, because we divide by the sum of our weights anyway, which we have to, because it doesn't help us anything that the smoothing kernel adds up to 1, because after all, we don't integrate the smoothing kernel everywhere, but only where we have data. So for this weighted sum to work properly, we need to multiply each y by the weight and then divide by the total number of weights. Notice that in a usual average, you have a 1 over n in front of it, and in a weighted average, you have a sum of the weights instead of a 1 over n. So the normal average gets recovered if you imagine the weight is 1 for each value. So this is what I've done here. I take this tricube kernel, and as you can see here, I have implemented if the absolute value is smaller than 1, it's this formula, otherwise we force it to 0. And now I can do my tricube smoothing, and that's what I've done here. I'd say this function here I can call and ask what is my value at x0, given the data values x and y and the smoothing bandwidth h. Now I first calculate the distance of each x to my interrogated smoothing point x0, divide this by the width, so I scale it into this area of -1 to 1, run it through the tricube, through this thing, get a bunch of weights, where these weights are 0 for all those values which are further away from x0 than h, and then I simply multiply element-wise the weights with the y values and divide by the sum of the weights. So this is our kernel smoothing function. In order to now actually use this function, I have to call it for many values of x. So I make me here a grid xg, which is just sequences from 0 to 1. And look like, I'm in the wrong thing here. Yes. So xg is just a list of 300 values going from 0 to 1 in steps of 1 over 300. And with this, Where am I? Help here. And with this, I can now do this. The supply function, you remember, takes each value, each of these 300 values and calls the kernel smooth function with this value as first argument and then adds the rest. So it's important, this function can only calculate the smoothing value for one x point, and we have to make a loop to call it for a grid of 300 x point things. I always call this xg for x grid. And now I go through it and I plot this, and what we now get is this here. The red points are my smooth kernel. The blue points is the original kernel. And you see it worked reasonably well. With one thing that we now have to think about it, what's the bandwidth? I used here bandwidth of 0.1. So what would you say would be, what happens if I make the bandwidth way too small? It gets very wiggly. Let's look at this quickly. I go here to my function. Plot, here we have them. Plot, here is the plot. Somebody give me a mouse. Oh, damn it. So here we have now this plot. I might want to add the original data points as well. Points x, y. So now you see here the original data points and the two curves. Now let's make the bandwidth much smaller. For example, 0.03. And what now happens is that each for each point, often only 2 or 3 points are under this thing, so that in the end, the kernel doesn't really, that the kernel becomes very wiggly, because whenever the random noise brings us up, the line follows up, and vice versa. Sometimes if we don't have enough points, we even get interruptions. On the other hand, if I make my kernel too big, then, as you can see, there's too many things, and simply because we average over too many points, the individual values get averaged out. So choosing kernel smoothing bandwidth is a bit of trial and error. There's a lot of heuristics about how to do this automatically, and thousands of papers with suggesting different heuristics, but none of them work really well. And for the automatic smoothing, that you always run into artifacts. If it's easy like this here, that the x-axis is nicely that the x values are uniformly chosen, you can of course say something like, okay, let's make the kernel such that we always have 20 points under it. But if this isn't, then we get into issues, and we'll see this in a moment. Now we can do this we can refine these things, because one aspect that you will always notice is that here, this thing it doesn't really manage to follow this steep decline. Among the steep decline, it's always a bit too high. And I would now want to improve on that by being able for this to follow this sudden dynamic changes better. And this is where local regression comes in. To do this local regression, let's have a look here what actually happens if I put an x0 and calculate my weight. I've done this here. I've chosen my x0 here at 0.4, just sort of at the end of a decline. And I want to see what are the weights here. And I found here this nice way to do that. As you can see, I calculated my weights, and now I plotted the points x, y. And I first plot them the normal way. That's what we always had. But now I use this text parameter, which is the size of the things, and use it such that the area of the circle show me the weight. And now, as you can see here at 0.4, what's sort of happening is that what we now sort of would like this thing to know is that our weight, that we just don't simply average over this thing, because we might end up here if we average because we are too high, but for it to sense that it's actually falling off and that we are on a slope. And here comes now the idea to, instead of simply taking an average over these y values weighted by these weights, we make a fit. And that's what I do here. I calculate, the LM function, which is simply a linear model. If I do this without this, it just makes a regression line in there, but the linear model can have weights. And that's what I've written here. So this is my linear model. I regress y and x, and I want to find two coefficients, a and b, to define a line, a plus bx, such that the points on this line, which I call y hat, go away, differ from the usual points y, squared up and added, and this sum of squares should be minimized. And in normal, ordinary least square, I try to minimize this sum of square as it is here, and in weighted least square, I put my weights in and say I want to minimize the weight of the sum so that the distance of that line has a stronger weight than the distance of that line. Here's a picture which shows you how this looks like. This is the regression line that I've just taken by using the results that I got from my fit. Let's put here, tell it here to actually write our fit line. And 4 and minus 9. So you see here intercept 4, slope minus 9. Intercept 4 should be somewhere up here, and then it goes down here. And as you can see, this line goes nicely through, and the middle of our kernel, where we put the highest weight, is here, and the fitted value that I now take is this one red value which sits here. And the orange line now follows that. And this is, of course, now slightly different than what we would have got if we take a simple mean. It's actually a little bit further down because the line is now made to follow this thing as best it can. So, and what we now do is we use, I use a new spoofing function. It starts as the same as before. I calculated my weight, but now instead of calling weighted mean, I call LM. And as you can see, LM takes here this weights argument. But then instead of using the whole line, I don't use the whole line. I only use the single fitted value where the line is at the center of the curve. So I take my intercept and my slope, multiply it with only x naught to only get the y value which is corresponding to the middle of the kernel, and forget the rest, and I return this. And then again, I use my sapply to call this function for everything of my 300 values with which I have made a grid from 0 to 1. And now, now I get this new curve here. And often this then helps us to get a better thing. Let's see if this makes a difference. Here, as you can see here, it's rather wide. And now with the linear regression, it sits a bit smoother, but it still has quite some issues following the curve well, which is of course also because it isn't well defined, because we have so few points here in this going down. You see, we have only 4. But nevertheless, this is how you can use this thing. Another reason why we can't follow this point so well is that, of course, we fitted a line, but here's a bend, and that's hard for a line to actually follow. You can already see this a bit here. It would have been nice if it had followed this curve here instead of just going straight. And this brings us to an obvious idea. Instead of fitting a line, let's fit a parabola. And fitting a parabola instead of a line is actually pretty simple. I just tell my LM I want to get a value not only for x, but also for x squared. And that's what I've done here. I added to x also an x squared, and for technical reasons which have to do with how R's formula looks, I have to put an I in front. And now R will try to make a least square fits for a parabola and gives me back 3 coefficients. 1, 2, 3. Let's see if we can actually quickly put this into the actual function here, which I put here. Here. That was my plot function, and here the orange line. And now instead of let's just mess here a bit by adding here a plus ix squared. Now I get with a fit, I get 3 parameters. And to see this here now, I have to now say, instead of AB lines, I have to say lines xg, comma, cof1 plus xg cof2 plus xg squared times cof3 and comma cal gleich orange. And now I should see here how you can now see the parabola actually follows these points nicer. Of course, here it's completely wrong, but that doesn't matter because in the end, we only take our value at this one point here where it sits. So let's add what we actually get here. Big up x2, not g naught. Because now the red point sits here, and as you see, it moved down. So this is now a slight variant. So we started from doing a simple mean under our kernel when we used the kernel weights to form a regression line, and now we even used a regression parabola. And I go back to the original thing, otherwise it doesn't fit to the text. And with this regression formula, now actually our red line follows this blue line surprisingly well. However, here we see a phenomenon which is called overfitting. It tries to follow the data too much, very much as what we had before when our bandwidth was too low. Here we also see something called edge effects, where trying to fit the parabola for a value here to Vx doesn't really work because it tries to use it can only use the right half of the kernel because to the left half there is no data. So overall, with this quadratic term, we've increased our smoothing quality here, but we got an overfitting here. So maybe we should go up with the bandwidth a bit, and we have to know that we can't trust the borders anymore. And when we now used this log-fit package, it does exactly these kind of things, plus a few more things. And now let's look at a few more things because we still have a bit of time. So here, higher order local regression, what I was. The next thing I want to look at is bootstrapping, because if we now look at such a formula and you notice here how it wiggles up and down, you might ask a bit about how sure am I that these wiggles are real and that they are not just overfitting and just an artifact of the data. And there's two ways of doing this to get some statistical confidence and some uncertainty value on your fitted value, and I want to show them to you. One is called bootstrapping. In bootstrapping, we do this here. We plot not one regression lines, but many of them. And we now see a spread of possible regression lines. And what I have done is for each of these 100 regression lines, I took my regression values and run my kernel smoothing. But I first did this here, sample it length x comma replace is true. What does this do? Sample int 10 gives me simply 10 values. And so it's a permutation of the values 1 to 10, every time a different one. If I do replace is true, it's no longer a permutation, but we are replacing it. In the sense of we have an urn of 10 numbered balls, we take out a ball, we remember its value, and for a usual permutation, you would then put the ball, take out the next ball. For a sampling with replacing, you place the ball back into the urn. Those who have gone to a German high school might remember this as ziehen mit zurücklegen. And in English, replacing, and it's important to stress, it's not a replace, but it's replace, because we are not replacing a defective part, but we are placing the ball back into the urn. So the sampling with replacing allows us that we can see the same number twice. Now, why does this make sense? And this is a general statistical strategy called Efron's bootstrap. Efron had the following idea at some point in the 70s. Usually in statistics, you use so-called parametric techniques to calculate an average. For example, if you calculate an average over a a couple of numbers and you want to know what is the standard error of this mean. The standard approach that you use is, you take the standard deviation and divide it by the square root of n. And this way of calculating the standard error of a mean, of course, makes an assumption, namely that your data is normally distributed. So typically in statistics, we make an assumption, namely that we know what distribution it is, for example, in normal, and that our calculation only tells us the parameters. In that case, the parameters of the normal are the mean and the standard deviation. And what we want to know is how good are our estimates of these parameters. What is the standard error of, for example, the parameter mean? But if we are not even sure that it's a normal distributed thing, this so-called parametric statistic is dangerous. And so there's this movement of using instead non-parametric statistics, which makes no assumption on what model we are using. And bootstrapping is a simple way of these non-parametric statistics, where we say we don't want to say what model we are using, what distribution it was. All we have is our actual data. And what is our best guess, our most general distribution that we can assume given some sample of data. And Efron argued, well, the sample is the distribution. If, for example, I have a die with 6 sides and I have seen 10 times with 1, 10 times with 2, but 20 times with 6, then I might argue that obviously this die has a probability that the 6 is 20 times as often. So if I want to simulate another throw of this die, I would just simulate drawing one value from the values of a die that I have just seen. If I want to simulate 20 dice, I just draw 20 numbers of those which I've already seen, but I'm drawing with replacement because we are simulating independent draws of a distribution. In independent draw, it shouldn't depend on what we have already drawn. This is why we are putting that back. So this is the general idea of sampling with replacement in order to get to see how your distribution can vary. And that's what we are doing here. All we have is our XY data pairs. And in order to get a potential new draw to see how might our smoothing curves change if we would have 100 new cells with new X and Y things, but we don't have 100 new cells, we only have these 100. Our best guess is to draw from these 100 another 100 XY value pairs, but with replacement, which will end up drawing a couple of values several times and others not at all. And then we can see what happens. And this is the most general way of getting an error distribution, sort of a feeling of how would our fit change if we had new data. Obviously, we will underestimate the amount of variation because we don't really see the whole breadth of possible new variation, but only a part of it. This is why we say the bootstrap sample is undervalued. Final question, why is it called bootstrapping? In the Germans among you might know the fairy tales of Baron Münchhausen, who at some point who always told this tall tales, they are called in English, Lügengeschichten in German, where he would have these tall tales about how he got himself out of pickles and difficult situations. At one point, he jumped with his horse into a morass, into a moor, and he soaked all the way up to here. And then in the German version of the story, he managed to pull himself out on his own hair. In the English version of the story, he pulled himself out of the bootstraps. The bootstraps being the straps which you have at the end of your riding boots to pull them up. So pulling out yourself at your bootstraps is an English idiom based on the story of Baron Münchhausen, meaning getting out of a situation using only the means that you have. And that's what Efron does here. We're only using the data we have without making any other assumption. We want to get an error. This is why in statistics we call this way bootstrapping, where we just sample from our data with replacement and rerun the whole analysis procedure. And now we get here something which tells us which areas the smooth is rather sure, like here, and where it is rather unsure, like here. You can actually then take for a given x value, you can just take the standard deviation of all the bootstrap values along this vertical line and call this the bootstrap standard error. And as I said, the bootstrap standard error will always be a bit lower than the standard error you would get if you had really new data, but it's good enough to get an expression. And it always works even if you have a complicated statistical issue. Here I have done the same for the quadratic regression, and you can see it looks much better in the middle, but it really have issues where the data is too low, and this will tell us here the bandwidth was definitely too small. Another possibility we can do besides the bootstrap is called cross-validation, and here specifically leave one out cross-validation, often abbreviated LOOCV, which is a complicated, a lengthy term for a simple concept, which is already in the name. We just remove one data point and run it again. And we specifically remove the data point we want to calculate it, because at the moment, when we take our smooth, at the position where we have an actual data point, we take this data point as the middle of our kernel. So the data we already have at this place has the highest value, which makes perfect sense. That we use that at the point where we have at an x value where we have an actual data point, we give this data point the most value. But in order to see how good the smoothing is, how much we can rely, how much we can tell from the neighborhood about the point itself, we could rerun the smoothing, removing this one point where we don't have it. So this is what I've done here. I go through all my x values, so not this time not through the grid xg, but through the 100 actual x values, and always run my kernel smooth function, asking it to calculate the smooth value at this position, but using all the data except for this one. You remember minus I in R means everything except for that one. And if I do this, then you can see here how every value now gets replaced by its corresponding value. And I can take this vertical distance between the two, call this now the residual, and I calculate my mean squared errors by taking these differences and square them and take the mean. And now I get a mean squared error, which tells us this thing. And one useful thing you can do with this is you can use this for bandwidth choice. By trying different bandwidths, now Andreas is gone, but this would have been one of his answers of one of the ways how to get a good bandwidth. There's an important caveat here, namely, you can use this for two ways. You can use it as for hyperparameter search, so find the right smoothing bandwidth by rerunning this calculation for different values of h and seeing which one gives us the lowest mean squared error. Or we can use this for precision analysis to give us a feeling about how good is our smoothing and report an error on the smoothing or an uncertainty on our smoothing. We must not, however, use the same cross-validation run to both. It is not allowed to use is to first find the best the first thing to find the best H and then report this as a smoothing thing. In order to do that, you have to do something called a nested cross-validation, which is a core concept of machine learning. But as we are not doing machine learning, I just leave it as here. If you want ever to use cross-validation, you must read up on nested cross-validation before going further. Otherwise, you make the standard mistake that you see in 80% of all biology papers trying to use machine learning. So here I've now tried how does this mean squared error differ between the simple kernel smoothing, where we simply take the mean, and the more advanced smoothing, where we use the quadratic regression. And as you can see, we go down from 0.016 to 0.013, so it helps a bit. But the problem at the edges make up the gain in the middle a bit. Next question, what happens if the x values are not uniformly distributed? You remember at the beginning, the x values were all uniformly drawn between 0 and 1. And what happens if they are not? And in order to do this, I tried to make a bit a strange X value, not drawing from some uniform, but from this complicated thing where I was playing around a bit to find something. And now I get here this plot where you can see here's an area where I have suddenly no data. And here I have lots of data. And if I now use this and run our quadratic smoothing thing, what will happen is, as you can see, the bandwidth is fine here and here, but here it's simply way too low. If I now increase the bandwidth, then I will probably lose this nice peak here. So I might increase the bandwidth to 0.3 to solve this issue here in the middle, but I will be unhappy about the bandwidth. And now here it looks better, but here it looks bad. How about if we made the bandwidth such that it adapts to the local density of points? If the points are dense, we have higher bandwidth, and if they are spread out, we have lower bandwidth. It can be easily done. Whenever we sit at a point and want to calculate the smoothing value here, we choose a bandwidth, and we choose the bandwidth such that we have enough data by just making the kernel wider and wider until it's wide enough to cover, let's say, 20 data points. And when we say now that's the bandwidth we use. Turns out that's quickly to program. Here is my quadratic regression function added with this thing. Instead of giving the bandwidth h, I now give the number of points that I want to have under the kernel. I call this hn, and I pass it, for example, 13 to say, always make the kernel wide enough that 30 points are under the kernel. So what I've done here is, to do this, I take the distances of all the points to my kernel and get the distances, and I sort this. And after I've sorted it, I have the distance to the closest, second closest, third closest, fourth closest. And then I simply take the 30th of these sorted values. So this is the distance to the 30th closest x value, closest to our integrated value x naught. This one's distance I call h. And then I go on as before, put this in my tricube, call my local regression, my linear model with a quadratic term, and get this thing. And now I get this curve here. And as you see, it now makes a good job of using the bandwidth it can have here and here, where the bandwidth is lower. It tries the best it can do. So now I have this last chapter. I think we make a 5-minute buffer, and then if you still have the energy, I can show you a little bit of how we get the Poisson noise into that. Are there questions for this? That gives us it. Yes. The worst thing is, of course, what I've done here is hugely inefficient, because I always calculate the kernel and the product over all data points instead of just saying where it's 0, I don't want it. So you can put a lot of work in this here. Yes. So if we do this in high dimensions, when we can use, of course, nearest, then of course this adaptive bandwidth will become extra important. Because when we do what we've done here is exactly what we already know from our nearest neighbor working. The question is now, again, if we use our first method, where we just say, let's just take the average, we get what's called nearest neighbor smoothing. We just take the 20 nearest neighbor cells, no matter which direction in PCA space, and average over this. But we can also do linear models in each principal component and see whether this makes things better. But now, yeah, thinking back a moment. In the beginning, we had this issue before, where we said, when we do this, okay, we have 21 minutes to go. Okay, but by then we probably want lunch anyway. Where we said here, you see here this distance from the way how this spreads between the zeros in those with 1 or 2 counts depends a lot on how we normalize. And if we normalize with 10 to the 5 instead of 10 to the 4, it all looks a bit different. And this is all a bit unfortunate, and we want to get over that. And another issue here is that we know that the precision of these values depend on how many counts we have. These values are more precise than those values here, because we've seen last time where is the Poisson noise has this instance where the more counts we have, the more precise the stuff is. So this means for us two things. We should make use of that fact in our smoothing. And you've already seen we used weights in our weighted means, but these weights should not only be the weights of it should not only be the weights of the kernel, but also the weights from the Poisson noise. And to do this, we do a couple of pre-studies before we get into the details. So, the first thing is something called inverse variance weighting. Let's imagine you have n independent random variables. It could be n Poisson distributed variables, and we want to estimate their mean. So we have these variables and we add them all up. So for example, it could be expression over 10 cells, which all have about the same pseudotime. And x is our log frag, and we want to add them all up. And we know that they're different, have different precision, because one cell might have a high sampling depth S and the other has a low sampling depth, so that the same fraction comes from different numbers of counts. And so when we do our average, we want to put weights on the average, putting a higher weight on the data which is more precise and a lower weight on the others. So let's say we know for each of these things their variance Vi. And obviously those with lower variance should be given higher weights. But how exactly should we choose these weights? And it turns out that we best choose the weights proportional to 1 over the variance. It's not obvious. It could also be 1 over the standard deviation or something like this. So why is it 1 over the variance? Here is the issue that we just have. We have, so I called it VI, the Wikipedia writes sigma squared, because sigma is the standard deviation. And as you can see, what they now suggest is that you weight each thing with 1 over V. And of course, when you have to normalize your weighted mean by dividing by the sum. So this here is exactly the same as what I've written here, with the WIs being 1 over VI. And how do you prove that? Well, let's not go through it because we are already too close to lunch to understand the proof involving Lagrange multipliers. But it's pretty straightforward, provided you remember how Lagrange multipliers work, which is something. Who remembers how Lagrange multipliers work? Who has ever learned how Lagrange multipliers work? Okay, I think I've learned it 5 times in my studies and kept forgetting and redoing it. Now I know it again after I've read this, but maybe do it another time. Maybe you want to look through it. It's a very nice little proof, but in the end, you notice, yes, it's really the variances that we have to take the inverse of. Now let's apply this to Poisson variables. And let's imagine we have a number of Poisson counts, Ki. And let's start first with a stupid thing. Let's say we have counts ki. As you might have seen in the notes, it just says ... because I thought I know this by heart. Let's see if I do this. So we have counts ki, and we have our corresponding si with this idea that ki is always following some Poisson distribution with some one and the same lambda, but each one has a different count, A because there's Poisson noise, and B because they all have different sizes. So this is my fraction, and I have to multiply the fraction with the total to get the expected count, and then I run it through the Poisson to add the noise. And what I now want to get is, I want to get an estimate of this lambda. And the simplest way to estimate this is that I take all these ki's, divide them by their si's, sum them up, and put here a 1 over n in front. And this is my normal thing. And now I want to use weights. And to get these weights, to make this sum more precise, I say let's weight each of these things with their corresponding with variance dependence. So what I do is I make my sum over ki divided by si times some weight, and I divide by the sum of all weights. And if we choose the weights cleverly now, we should get something better here. And we should now say, we know here that the variance of this, the variance of ki is si lambda. This means that the weights should be, according to the invariance variance logic, 1 over the variance of the counts. So it should be proportional to 1 over si. Why proportional to? So that I can remove the lambda because I don't know lambda, but it doesn't matter whether I have a lambda because it's proportional anyway, because we normalize the weights in the end anyway. So if I had this lambda in here, it would cancel out. So I take this, I write what I have here. I now say here ki over si, and the variance is 1 over si. So the weight should be, what have I done here now? Well, weights 1 over si. And here I have this 1 over si. And now it doesn't cancel as it should. I'm missing an inverse. Who finds the missing inverse? The variance is, because in the end I was hoping to get to the results that instead of taking the mean of a fraction, it's better to take the fraction of the means and sum things up like this. And you get this by saying, here something is wrong, because, of course, I've seen it. This is the variance of ki. Now we have to ask, what is the variance of ki over si? And this is now the variance of ki 1 over si squared. Why? Because if I have a constant, I pull it in front of the variance operator, it gets squared. If you remember how the formula for the variance looks like, you can see that there is a square, and of course, if I pull it out, I have this here. So, and the variance of ki is when 1 over Si squared, and the variance of ki is Si lambda, and this is of course proportional to 1 over Si, which makes sense. So this is what we now get, and then the weights should hence be proportional to SA, which makes sense. We should put more weights on the big cells where we have high counts. Which is an interesting general effect. Whenever we work with these fractions, we are better off not taking the fractions and taking the mean of the fractions, but rather adding up the counts and the totals separately and then dividing. Why does this now here stand on take a photo? The hope was actually that it stands on video so that people can see on the work, whatever. So there was an error playing the video. I don't want to play a video from the webcam. I want to just get this to just take a picture of the board. Okay, it doesn't help. I have to take a picture afterwards and link it to it. So, and this is one thing, and an effect of this is if we were to smooth our counts, we should now use this logic and calculate and do a Poisson smooth. And if we do our kernel smoothing with a Poisson, we should now say before we said kernel smoothing, we use our weights, so the kernel fk von x minus x naught over h times y divided by this thing xi minus x naught over h. This was how we did the kernel smoother before. And if we now were to use this for Poisson distributed data, so if this YA, if that would be now some Ki over Si, with Ki being Poisson distributed, then we should put the Ki here on top and the Si here at the bottom to get a good smoothing. And we can try this later and see how this works. And I can already show you ahead a little bit of how we get with that. So local regression with GLMs, is this the right place? Here I took my data. No, I haven't done this yet. You can try this as a homework. Take our glass data, use the glass data, do the smoothing and try once using the smoothing techniques we've done before, and second, try the smoothing with this kind of logic, where you say put the counts on the top and the S at the bottom, and see what you get there. Yes. Yeah. They're actually on a GitHub repo. I only have to give you the link to it. So now maybe the GLMs we do next time. Who knows about generalized linear models? Okay, then we do this next time. But what they do have for you for a thing is a homework. The first thing is this kind of, here's our regression line for solute carrier 2A1. And as I said, I used it here with log fit. You can try to do now this regression line, not using log fit, but using our manual kernel smoothing, and try doing it either by putting the fraction as here on top or putting it as a whole thing. Check whether you need adaptive bandwidth or not. Probably we will need adaptive bandwidth because it's very uneven. And check whether, what else do we need? We need adaptive bandwidth. We probably will also profit of using the quadratic thing. So we can use our final function where we put it all together, the adaptive bandwidth, the quadratic, regression, and so on. But we have to add this one thing of splitting the counts and the size factors between top and bottom to get something. And then, of course, once you plot the result, you will have to wonder what should you plot it on a normal axis or on a logarithmic axis. And when we still haven't solved this 10 to the minus 4 problem, for that we need the GLNs. That's, I noticed I didn't get as far as I expected, but we will get to this. Now, one gene is no gene, and we might now ask, how do other genes work? Do they all look like this? So we can use 10 or 20 such genes, which might behave because some genes might go down, others might go up. So we might want to make such a curve and make a plot which has this curve not for one gene, but for 20 interesting genes. And to find the interesting gene, let's just look for genes where the expression differs a lot between here and here. A couple of maybe 5 genes which go up strongly from this blob to that blob. To find them, you can go back to the clusters. Take this cluster, take that cluster, calculate the log fold change between both of them, pick the genes with the highest log fold change up and down. So by log fold change, I mean the ratio between here and here, between this mean and that mean. And then how do we plot these 20 genes? That we found one way is to make this plot here simply with 20 colored lines all on top of each other. Another way, which is quite popular, is to make this thing a ribbon. So instead of plotting it like this, we plot it with color, using lots of color here and a bit of color here. And the way how you do this is you just call the heat map function or the image function, giving it only your one row of things, so that it uses the y-axis, not, actually you can do it in ggplot. Instead of geom line, you use geom tile and tell it, geom tile, this is the x-axis, the y-axis is simply constant 0, and the color is what used to be the y-axis. And then instead of making this constant 0, you can give the y-axis as the gene name, so it makes these color ribbons below each other, so that we get a colorful plot of several of them. And then you get this trajectory heat map where you can see which genes go up and which go down and so on. And yeah. And of course, for this, you have to make a grid of your x-axis into maybe something like 100 values, so that you get 100 little pixels of different colors. So this was here my first homework. And what have I've written the second homework was what I've just already mentioned. Here we have our x-axis is just the pseudotime. So we assume that the pseudotime perfectly determines the value. So in other words, the value of slack of glass depends on our progression along this line, but it doesn't depend on the difference across perpendicular to the pseudotime. This is of course not true. It might depend on that. So an alternative is what we've just already mentioned, is to use nearest neighbor smoothing. For each cell, take its 20 nearest neighbors, which we probably still find in our old data from last time. And these 20 nearest neighbors, calculate the average of these 20 nearest neighbors. You can calculate the average either by simply doing this k over s, or you can calculate the average by using a smoothing kernel, by putting, multiplying this also with here instead of this. Here you just consider this as the Euclidean distance between the point, the cell that we want to smooth and the stuff around. So x naught is the cell's PC coordinate and xi are its 20 neighbors, and then you do this. The difference will not be great because the smoothing value will not vary that much, probably because, as we already said last time, the distances are all the same. The last thing, okay, we haven't got that far, because this is probably the homework for the next time, because we want to know how well does this neighbor smoothing work. And instead of doing this, we do leave one out smoothing. Calculate the sum once including the cell itself and once not including, or calculate the sum smoothing only over the neighbors without adding the cell itself, and compare with the cell's actual value and see how far away you're from that. Then you can even color your cells by that in order to see where your smoothing works well and where your smoothing doesn't work well. So, yep, 11:58. That's a good time to finish. And then we can see where we go that. So with smoothing, as you've seen, it's simple math. We haven't yet gone beyond least squares. Even for in the generalized least things, we generalize away from that. The trick is always to remember what are we looping over, and what is the value and what is the neighborhood and so on. We actually implement this, it can get a bit complicated. So. Ja, Habe Come. Ja. Jo. Dann schön, wenn du Lust hast, komm mal vorbei.
Bist du eigentlich am Donnerstag am Ende, beim Single Cell Club oder?
Tschüss. Ja, ich bin am Single Cell Club, aber ich habe vergessen, dass das am Ende ist. Wie kommen wir denn da hoch?
Es gibt einen Bus.
Es gibt einen Bus.
Ja.
Da muss ich mich registrieren, ja gut. So. Nee, haben wir wieder die Mail nicht gelesen. Okay, ja, wenn. Ja, nee. Du hast schon dich auf den Bus geschrieben. Du stehst schon auf dem Bus.
Ja, also ich habe
immer falsch. Ach, den ihr Bus, aber der ist doch immer schön groß gewesen, der Bus.
Er ist bestimmt.
Ja. So, jetzt muss ich mal schauen, das ist dieses Mal hier. Wenn